Hi guys! Today we're going to be talking about valence electrons and how we can use a number of valence electrons to talk about Lewis dot structures. So first we just want to quickly go over what valence electrons are. And they are the outermost electrons in an atom. So they're going to be the atom's outermost electrons, and they're always in our s and p orbitals. Valence electrons are important to us in chemistry because they determine when an element or an atom is going to participate in chemical bonding, and they tell us the chemical properties of that element. So basically the whole rest of the year has to do with electrons and how they interact with each other. And like I said, they're the outermost or highest principal energy level, S and P electrons. So for example, down here we have beryllium, nitrogen, and neon. And you can see that I wrote the electron configurations for these. And if we look at the outermost S electrons, they're the ones right here in this second principal energy level. So beryllium has 2 valence electrons. Nitrogen is going to have all of these electrons in the outermost S and P orbitals. So that is going to be 5 valence electrons. And then neon is going to have these, and also in its second energy level for the S and P orbitals are going to have a total of 8 valence electrons. Now the maximum number of valence electrons that we can have is 8, and that is because that's the maximum number of electrons that could be held in an S and P orbital.
So we can use these electron configurations to figure out the number of valence electrons that an atom will have, or we can actually just use the periodic table to determine the number of valence electrons. So the important thing to know here is that elements in the same group, and by that we mean the same column, elements in the same group have the same number of valence electrons. So every element under hydrogen has the same number. Every element under beryllium has the same number. The way we read the periodic table to determine the number of valence electrons is that hydrogen's group all has 1 valence electron. These are the alkaline metals. Alkaline earth metals, under beryllium, they all have 2 valence electrons. We have a 2 written up here. At boron's group, we have 3 valence electrons. Carbon's group has 4 valence electrons. Nitrogen's group has 5. Oxygen's group has 6. Fluorine's group, which we call the halogens, they all have 7 valence electrons. And the very last group or column, we call these the noble gases, they all have 8 valence electrons, except for helium. Now remember, helium actually belongs over here in our S block. It has 2 valence electrons. The reason it's over here is because it has the properties of the noble gases, since its outer valence shell is full and happy with just 2 electrons. So it has the properties of these noble gases.
And that's because it only has an s orbital. It doesn't have any p orbitals.
Right. So there's a maximum of 8 valence electrons, and that's what Ms. Thomas was saying, 8 valence electrons, because that's the max number that can fit in an s and a p orbital. So 2 in the s, 6 in the p, that's a total of 8 valence electrons. We also have a table here that just kind of shows you for each of the, if we're looking at elements here, what group they're in and the number of valence electrons. So group 1, 1 valence electron. Group 2, 2 valence electrons. And then we jump to 13, which has 3 valence, 14 has 4, 15, 5, 16, 6, 17, 7, and 18, 8 valence electrons.
Okay. So one of the reasons why we care about valence electrons is because we use them to draw what we call Lewis electron dot structures, and those to help lead into chemical bonding, which is the next unit that we start at the end of the semester and then continue with next year. So really important, I know that you guys some of you learned how to make Lewis dot structures in middle school, and you learned how to make them for molecules and for the bonding, which we are going to be getting to, I promise. But right now, we are just drawing them for atoms, which means we care about where the dots go and when, and I know that we are very strict about it, but we have a good reason, and we will tell you about it in a second. So we are drawing Lewis dot structures for atoms, not molecules. And that's what it says up there. There's a shadow, so it's hard to see. Sorry. Okay. The Lewis dot structures show the chemical symbol of an atom surrounded by the number of valence electrons. And like I said, we do need to put those valence electrons in a specific order. So these are the steps for making a Lewis dot structure. It's very straightforward. The first thing we do is write the chemical symbol and determine the number of valence electrons. So the chemical symbol, this is just a general example right here, would be X. And then for this, I have 8 valence electrons. So we would pretend that this element has 8 valence electrons. And remember, I can use the periodic table to figure that out depending on the group. Second thing is I pair my first 2 electrons on the right. And that's because it represents the off-bow principle. Electrons are always going to enter the orbital with the lowest energy first, and they'll fill up that orbital before going up the stairs like we saw in the Poggle. So this orbital right here, these first 2 electrons on that right side, that represents our s orbital all the time, and we only have 1 of those. Okay? And then the third step is to fill the rest of the electrons as singles until they double up, and that's Hund's rule, right? Electrons not only are lazy, but they are also going to be selfish and antisocial, and so they are each going to go in their 1 orbital, and then we're going to go back around again and only double up when we have to. So they're going to be antisocial in that sense. So for this, I would have drawn the dots in this order. 1, 2, 3, 4, 5, 6, 7, 8. So these are my p orbitals. Let's say this is px, py, and pz.
All right, so we can actually do some examples over here. We have magnesium, and we actually, from the electron configuration, can see how many valence electrons it has, right? 3 is our furthest energy level from the nucleus. So however many electrons are in that 3 energy level are the number of valence electrons, which is 2. You can also use the periodic table.
You can see magnesium is right here, and it has 2 valence electrons.
All right, so 2 valence electrons, we're going to draw our chemical symbol. We know that there's 2 valence electrons, so we have to add those 2 in. Remember that our first 2 electrons are going to pair on the right side because that's our s orbital. And there's magnesium. For phosphorus, our chemical symbol is P. If you look on the periodic table,
Is right here, so it's going to have 5.
or you can look at the electron configuration and see an energy level 3, which is the furthest from the nucleus. We have 2 plus 3, which is 5. So we're going to add our 2 here paired, and then we go top, left, bottom, right? There's phosphorus with its 5 valence electrons. And last, we have argon. Ar is our chemical symbol. On the periodic table, it's in the noble gases, so it has 8 valence electrons. We can also see that here in energy level 3. And then we pair our 2 valence electrons first on the right, and then we go top, left, bottom, top, left, bottom, and we have our 8 valence electrons drawn.
I just want to point out this is very similar. The filling of the dots is going to be just like we filled in the arrows for the orbital notation, or the orbital notation. So it's just the exact same pattern. That's all we have for you guys today. Thanks for watching.